Okay, I want to cover one last concept or tool in this module of control systems, and that is the Final Value Theorem. What is it? It says if you're interested in the limit of a time function as time goes to infinity, you can find it directly from the Laplace transform of that function by multiplying it by s and taking the limit as s goes to 0. What that means is, if you're only interested in this limit, you don't have to take the full inverse Laplace transform to find that limit. We just did a couple of examples. Here we wanted to find the limit. Just say if all we wanted was to find this limit. What is this y of t as t goes to infinity, as time goes to infinity, where we're given the transfer function and the input? We had to do this fairly tedious inverse Laplace transform using partial fraction expansion to get the function and then take the limit. Finally, you could take the limit of this answer, and the answer was 1. We did another example if we had to find the same limit. Here was the overall answer, but as t goes to infinity, this decaying exponential goes to 0, and it just becomes 1 out at the limit. But if all you were interested in was that limit, you could have avoided all this work. So that's the benefit of this final value theorem. If you want a derivation of this, see my lecture notes for NMath A on my website. But there's a caveat to this. This whole function here, s times f of s, it can't have any poles, or all its poles must be strictly in the left half plane, left half of the complex plane. Poles are the denominator of this thing. The denominator set to 0, that's an equation. The poles are the s's that make that denominator go to 0, or be 0. So look at this. If you're interested in an output when the input is a unit step. Let's say we're interested in the steady state output and the input is a step. What is a step? It's just 0 for time less than 0 and the constant 1 after time 0. Probably should have provided a graph. It goes beep, beep, beep. Well, the Laplace transform of a unit step is just 1 over s. You look at the output, it's transfer function times the Laplace transform of the input. And the input's a unit step, it's just 1 over s. That means the limit of the time function of y is s times this big Y, which is g times 1 over s. The s is canceled, and the answer is just the transfer function evaluated at 0. You want to know the steady state response to a step, all you need is the transfer function, at least when this limit exists. Let's look at our prototype systems to a unit step. Here was the prototype first order system. What is it? What is its steady state response to a unit step? We just plug in 0 for s. It's 1. That's why we scaled this guy to be that way. We wanted to normalize it. We wanted the steady state output to be 1. Here's the the prototype second order system. Give it a unit step input. As time goes to infinity, put in 0 here. Get omega sub n squared over omega sub n squared. That's 1. Again, normalized to 1, and we defined them that way. How about some other examples? If these are the transfer functions. First, the poles have to be strictly in the left half plane. What are the poles of this? It has a single real pole at -3. S plus 3 equals 0. The root of that is S equals -3. So it qualifies. Plug in 0 for S, you get 1/3. Put a unit step into this system with this transfer function in steady state, it goes to 1/3. What about this guy? He has complex poles, but the real part is strictly negative. We don't care about the complex. Plug in 0 for S, you get 5/2. Steady state value as time goes to infinity. Output of this. This guy. This guy has poles exactly on the imaginary axis. That does not qualify. That is not strictly in the left half plane. It's on the imaginary axis. So we can't apply the final value theorem for this guy. I'll look at it anyway. I'm not going to go through this in detail. But if this were the transfer function, you put a unit step into it. You got to do some partial fraction expansion, yada, yada. You get this response. This doesn't have a limit. There's constant oscillation. So, and that tells you why you can't just blindly apply the final value theorem. You got to make sure all the poles are strictly in the left hand. What about inputs other than unit step? This is what we mean by a ramp input. And we're going to be talking about standard inputs more throughout the course. Impulse is a standard input, a unit step is, a ramp is, and there'll be others. This is a ramp. Its Laplace transform is 1/s². So if you multiply these two guys together in this case, it's g(s)/s². To apply the final value theorem, only you still have an s in the denominator. So it's not just as easy as plugging in 0 in the transfer function. You have to actually go through this. So what about this first order prototype system? I put in a ramp. The limit of the output as time goes to infinity is this guy, E/s. So there's this extra s here. That's a pole at 0, which is not the pole at the origin, which is on the imaginary axis. It's not strictly in the left half plane, so we can't apply the final value theorem here. In fact, the output will go off to infinity. What about the second order prototype? Oh, this isn't the second order prototype. It has an s in the numerator instead of (n²). Its limit, the output of this system, E divided by S, those s's will cancel and you just have this. Now you could apply it. Well, assuming the zeta and omega n cause if they're both positive, we're okay. Then the poles will be strictly in the left half plane. And plug in 0 for S, you get 1/omega(n²). Yeah, this isn't quite a prototype second order. What about impulse response? There, that means the input in the Laplace domain is just 1. Output is, or the limit of the output is the limit of S times the transfer function. Let's apply them to, here's the prototype first order system. Take that and multiply it by S. If that's in the numerator, that's just going to go to 0. So if I ping a first order system with an impulse, it'll settle back to 0 as time goes to infinity. What about the prototype second order system? Take this transfer function and multiply by s. I get s in the numerator. Plug in s equals 0. I'm going to get 0 again. These guys will settle back to 0, assuming the tau and the zeta omega n are positive. Then the poles will be in the left-hand plane. So to finish up this whole module, just a reminder of some of the key concepts we defined here and which will be important throughout the course. We'll talk more about them. These are key, not just throwaway ideas. The transfer function itself, fundamental. The characteristic equation, fundamental. The characteristic equation tells you where the poles are, which are where the poles are in the complex plane will tell us later many aspects of the dynamic behavior of the system. So will the zeros, which are, those make the numerator of the transfer function go to 0. We talked about the impulse response, weighting function, and actually these two are the same thing. The impulse, and in fact, both of them are the inverse Laplace transform of the transfer function. Talked about prototype first and second order systems. We're going to be discussing a whole lot about them. And then finally, we just wrapped up with the final value. Anyway, that wraps up Module 2 of my control systems course. See you for Module 3 sometime.